Hello, myself Naveen Kumar Saini. In the course Electromagnetic Field Theory, code KEE 301. Today we are going to start Unit 5. So which comprise waves and the applications. So in that Unit 5, as per the syllabus, so these are the content which we are going to follow. That is wave propagation in the loss dielectrics, plane wave in lossless dielectrics, plane wave in the free space, plane waves in good conductors, point power and the Poynting vector, reflection of a plane wave, transmission line Smith chart. So before going into it, we must know what is the difference when we talk about the waves, right? So till now, we have discussed about the electrostatic and the magnetostatic. So as the reasons behind that in electrostatic and the magnetostatic is, first difference is the stationary, so here, sorry. So in that, so reason behind the electrostatic, that is the stationary charges. As I said before, when the charge is present in the space, so because of that charge presence, there is a electric field will be present there. And for that, the electric field can be defined in particular position, that is XYZ. So it is not the time varying field. Okay. Second is the steady current is the source or the reason for the magnetostatic field, where it signifies H XYZ position. Third one is the time varying current are the reasons for the electromagnetic field or the waves. So in that, here the component that is T is involved into it. Okay. So stationary charges, electrostatic field, steady current, or the charges are moving into the concave conductor with the constant velocity. So there is no acceleration and it will not change with time. So that is the H, X, Y, Z. And then we have third component, that is time varying component. So time varying component are introduced into E and H. So that is your E, X, Y, Z and T, and H, X, Y, Z and T. So this is the reason behind for generation of the waves into the system, right? So in that, any example for that is time varying fields. Examples are any pulsating current which is accelerated or deaccelerated. So in that way, these examples are represented here. Sine waves for the first example for that. Second is the rectangular pulse waves which is traveled and it is changing with time. And third one is triangular wave. Okay. So these three are the pulsating currents which are responsible for generation of the electromagnetic waves. And we are aware also about that waves can be generated or forwarded from one point to another point when we have the component that is T is involved into it. If T component is not involved, then the waves cannot be propagated from one point to the another point. So there are basically two major two concepts which we are going to discuss here. First is the electromotive forces, which is completely based on the Faraday's experiment. Okay, so this is the first major concept which we are going to discuss. Second is the displacement current. So this displacement current is basically completely based on the hypothesis. There is a Maxwell's hypothesis. So whatever equations which we have up to now, which we have discussed. Okay, so what the Maxwell's equation which we have discussed till now. So first Maxwell equation, that is del dot D is equal to rho V, del cross E is equal to 0. Then that is the del dot B is equal to 0 and del cross H is equal to J. So these are the four Maxwell's equations which is completely based on the static fields. Okay, so these are the Maxwell's equations. Maxwell's equations in static E and H field. Okay. So now there is some of the modifications are there into these equations. So two equations, equation number 1 and the equation number 3 will be the same, but the modification will occur into the equation number 2, that is del cross E is equal to 0, and this one del cross of H is equal to J. Okay. So the modification will occur only in these two equations when we talk about the time varying fields. So as we are very much aware about that, this del dot D is the scalar quantity, right? So there is no direction is involved into it, there is no change as per the time. Del dot B, these equations is a non existence of monopoles. Also these are definitions for that. So the modification will occur in these two equations, del cross E and del cross of H. So based on this, we will discuss into the complete unit 5. So how the modification will occur into the Maxwell's equations, and we will take care about that. So first one is, as we said, based on the Faraday's law, right? So as till now we have we know that the concept which we have when we have when we have the current carrying conductor, right? So when we say the current carrying, due to the current carrying conductor, the current is already flowing into the current carrying conductor, because of that one the magnetic field will be generated. Now opposite of that, when the magnetic field is there, so because of presence of the magnetic field, the how the current will be generated. Okay. So this is the concept which they have discovered based on the Faraday's law. So according to the Faraday's law experiment, so a static magnetic field which produces no current flow, but in the closed circuit a time varying field which produces the induced voltage, that is called the electromotive forces, or simply EMF. Okay. So which is the cause of the flow of the, which causes the flow of current. So the presence of the magnetic field in the time varying field, the current flow will occur. So these are the opposite of that one which we have just discussed in the previous cases, just like the our Biot-Savart's law. When we have the current carrying conductor, so into this current carrying conductor, due to this current carrying conductor, we have calculated the value of H, right? And opposite of that, when we have the time varying magnetic field, so because of the current magnetic field, we have induced the voltage into the given loop. So this is the loop, right? So into this loop the EMF will be generated. So as per the Faraday's law, what it says, the Faraday's law discovered that the induced potential difference or the electromotive force EMF in any closed circuit, so this is very important point, is not for the open circuit, for the closed circuit, is equal to the time rate of change of the magnetic flux linkage by the circuit. So in that expression we can write that V EMF is equal to, with the minus sign, d lambda upon dt. So lambda is nothing but this is the total flux linkage by the closed circuit. Okay. So this is for the closed circuit. So when we have n number of turns into that closed, when we have the n number of closed circuits or the closed turns, so in that case total flux lambda will be equal to n times of the psi. Okay. So n is number of this is the total number of the loop, total number of loops or the circuits, loops or closed circuits. Okay. And lambda or psi is nothing but the flux linkage by the single loop. Okay. So similar to that, when we have n number of loops, so in total flux linkage will be equal to lambda, that is n psi. Okay. So in place of psi, as we have discussed in the Biot-Savart's law as well, when we are going through it, the flux linkage by a single flux loop is equal to B dot ds, open surface. So keep in mind that we cannot put the circle here, right? So here this is psi is equal to B dot ds. So what it says, for a closed circuit whose surface area is ds and the magnetic field which is passing through that surface area, that is B. So in that case, total flux will be equal to psi is equal to B dot ds with the open surface. So here the negative sign is representing, it shows that the induced voltage which act in such a way as to oppose the flux producing it. So this behavior is described by the Lenz laws. Okay, Lenz law. Okay, so this is given by the Faraday's law. Okay, so where we say that when we put the closed circuit into the existing magnetic field, so what will happen in the closed circuit, the EMF will be generated, and this total if we have n number of closed circuits or the open loop or the loops, then we say that total flux will be equal to lambda is equal to n times of the n psi, and psi is for the single loop flux linkage, that is B dot ds. This is for the one loop. So similar to that, when we have the n number of loops, so it will become the n lambda is equal to n psi. So now by using this Faraday's law, we will discuss how the magnetic voltage will be induced into it. So for that one, there are two more concepts which come into the picture, that is the transformer and the motional EMFs, okay, or the electromotive forces, or the two EMFs will be there. First is for the transformer EMF and second one will be for the motional EMF. So how this transformer or motional EMF will generated? It is based on the basically conditions. Okay, so the conditions may be like when we have the one loop is there and the second flux lines are there, or the magnetic field is there. So if the loop is stationary and field is varying, is the first case. Second case is when the loop is moving and the magnetic flux lines are constant or stationary, or third case maybe both are varying. So one of the thing must be varying to generate the transformer or the motional EMF. So motional this EMF can be generated when we have the time varying fields or the moving or the closed loop or the circuits are in motion. So as I said, the three types of transformers are there. So it is apparent that EMF can be generated in the closed loop. So this is a condition for that, because circuit will be complete when it is the closed, then only the current will be flow. If for the open circuit, current will not be flow. Okay, so in this case, any of the three conditions can occur. So first case will be a time varying magnetic field. So B field is varying, which is linking a stationary loop. Okay, so this is the first case where the loop is stationary and the time varying field is there. So as the time varying field is there, so it what will happen, the flux linkage rate will be different. So because of change of flux linkage, the EMF will be generated. So this type of EMF is called the transformer EMF. Correct? Second case, when we have the loop is moving and the magnetic field is the constant or the static magnetic field and loop is moving. So in this case, what will happen? The motional EMF will be there. So a loop, a moving loop, right? In the previous case, we have the stationary loop. Here we have the moving loop with a time varying surface area in a static field. So this type the induced EMF, which we call it, that is the motional EMF. Okay, so this is the second case, and third case is when we have the loop and we have the magnetic field, both are varying. So when both are varying, in this case what will happen, the flux linkage will be changed, the rate of flux linkage will be changed, and because of that the EMF will be generated. So total EMF in this case will be the VEMF is equal to VEMF transformer and the VEMF motional. So in the both the EMFs, or the transformer EMF and the motional EMF, will be there in the third case. Okay, so this is the main thing which you have to take care of about the generating the EMF when we have the loop and the field is both are varying. Okay, so in this equation we see, when we talk about the first case, time varying magnetic field which is linkage with the stationary loop. So in this case there is no motional EMF. So in this case we know that V EMF motional will be equal to 0 because we have the stationary loop. And in the second case, V EMF transformer, this will be 0, right? But in the third case we will have both EMF transformer plus V EMF motional. Okay, so both type of EMFs will be present into it. So here we see for the stationary loop V EMF motional is 0, and for static field V EMF transformer is 0. So here from the previous equation we can use this V EMF, that is minus d lambda upon dt, and that is equal to n minus n d psi upon dt, and psi is nothing but b dot ds. So negative sign in this expression which shows the induced voltage acts in such a way as to oppose the flux producing it, and this is called the Lenz's law, and it emphasizes that the direction of current flow in the circuit is such that the induced magnetic field be produced by the induced current will oppose the change in the original B field. Okay. So let's come for the, we will get what the expression for the first case where the stationary loop in time varying B field. Okay. So in this case the EMF which is generated, that is the transformer EMF. So it shows the diagram that induced EMF due to the stationary loop in the time varying B field. So this is the B field in which the B field is changing with time, so it is increasing. So in this case we can use this equation that V EMF. So in the previous case we can see V EMF is equal to n times d upon dt B dot ds. So here we see n in this case when we have a single loop, so the value of n will be 1. Okay, and V EMF, we know this formula, that is E dot dl with the closed line, and that is equivalent to minus del B upon del T. So here we can see. So as we said V EMF, here we can write that V EMF is equal to n times of d upon dt integration B dot ds. So we have written it from this equation, right, with the open surface. So here in this case, because we have the loop, one loop is there, so n is equal to 1. So what this equation will become, 1 minus n is 1, and we can take this differentiation inside that, then it will be equal to minus sine del B upon del T dot ds. Okay. So now V EMF is equal to this one. So here we can write V EMF is equal to this one, and we are aware about the in electrostatic that V voltage, change in voltage or the voltage difference is equal to E dot ds with the closed path. So I will suggest you please go to the previous lectures to understand this concept, and I have already discussed about that when we have the closed path. So in that case the voltage will be equal to E dot ds with the closed path, and that, okay. So now what we can do, so we have this equation now. So for this equation we can apply the, because this is the closed path. So when we have the closed path, so we can apply the Stokes theorem for this case. So we can apply the Stokes theorem in the left hand side, Stokes theorem. So when you apply the Stokes theorem, so E dot dl with the closed path is equal to the open surface del cross E dot ds. Okay. So this concept also we have discussed in the Stokes theorem when we have derived that. So that E dot dl with the closed path is equal to del cross E dot ds. So we are just simply applying the Stokes theorem only onto this part, right? So this is the expression which we get. Closed path equivalent to the open surface in the case of Stokes theorem. In the divergence theorem, what happened? We have the closed surface will be equal to the volume, right? but we are taking the closed path. So that is equal to the open surface. Okay, so now this is equal to this one. So this is this equation. So just compare these two equations. Then when we compare it, then del cross E will be equal to minus del B upon del T. So this is the modified equation in the time varying B field. Okay. So in the static field, what we have the equation, you can see here. In the first case, we have discussed that del cross E was equal to 0 when we have the static electric magnetic field. But now this is changed, del cross E is equal to minus del B upon del T. So here if B is a time varying field, so B is changing with the time. If again the B is constant, B is static field, so del upon del T into B will be 0. So again it will become del cross E is equal to 0. So here because we are taking the time varying B field, so because of that one, del cross E is equal to minus del B upon del T. So this is the Maxwell's equation. So we can say this is the Maxwell's equation. Maxwell's equations in time varying B field. Okay. So this is the Maxwell's equation in time varying B field. So del cross E is equal to minus del B upon del T. So this is the case of non-conservative nature. So this is nothing. This is the non-conservative nature. So this is the case for the non-conservative nature. We call this condition non-conservative nature of the electric field. Okay. So del cross E is equal to 0, then conservative nature is there. Del cross E is not equal to 0, so that is equal to minus del B upon del T. So this is the case of the non-conservative nature of the electric field when we have the time varying B field. So here how the when the B field is changing, so how the flux rate will change. So if the original B field is increasing, this what is the meaning of that, that del psi upon del T will be greater than 0. So this is according to the Lenz's law, and here that I has to be in the direction shown in the order of B induced to be in the opposite of B B time varying B field. So as a consequence, terminal 2, which we have discussed in the previous diagram, that it would be at high potential and EMF would be at negative value. As the B value is increasing, the V value will be increased in the opposite direction. So if the BT were to be remain the same direction but decrease in the magnitude, so if the magnetic field is decreasing, so in this case the rate of change of flux lines will be also be decreasing. So in this case the current would have to be reverse of the direction of that, and its induced field B induced would be the same direction as BT as to oppose the change in the B. Okay. So here it is to be remember that B induced which serves to oppose the change in BT. Okay, and not necessarily BT itself. Okay. So in all view we see that B induced will affected when we are changing if the rate of flux lines are increasing or decreasing. Now come to the second case. The second case is the moving loop into the static B field. Okay. So in this way, because we have static B field and EMF which is generated by the moving of the loop is called the motional EMF. So here when the conducting loop is moving into the static wave field, so this is the very important condition for the motional EMF. Okay. So an EMF is induced into the loop, and the force on the charge moving with the uniform velocity will in the magnetic field is given by the V and the Fm is equal to Q into U cross B. So this Q U cross B is there. So what it shows, when the loop is moving, so in this case the force will moving with the velocity of U in the static B field. So okay, so in this case the total force will be what? So this force is called the magnetic force. This force is the magnetic force. Magnetic force. Okay. So this is the magnetic force Fm is equal to Q U cross B. So we define the motional EMF or motional electric field, that is the EM. So EM is what? The formula which we are aware that electric field is given by the force per unit charge. Okay. So this is the definition of the electric field. So motional electric field will become Fm upon Q. So this is Fm upon Q. So just divide this with the to Fm. So it will equal to U cross of B. EM is equal to Fm upon Q is equal to U cross B. So U is what? U is the motion of the charges into the loop, or the loop when it is moving with the velocity of U. Okay, loop is moving with the velocity of U and into the magnetic field. So B is the static magnetic field. So in this case, we can little bit modify the previous equation where we know the formula for V, that is equal to, this is our general formula which we are very much aware about this. Okay, E dot dl. So electric field which is which is motional in nature. So here we define E, we can define this E as the EM. Okay, so here EMF is called the VEMF. So this is the VEMF is equal to EM dot dl. Okay, so this is the case. So here in place of EM we can put U cross B. So in place of EM we can put the U cross of B dot dl. So this type of EMF is called the motional EMF or the flux cutting edge, or the flux cutting EMF, because it is the due to the motional action of the loop into the static magnetic field. Okay, so this kind of EMFs are present into the electrical machines, maybe in the motors, generators and the alternators. So these are the example into which the motional EMFs are generated. Third case is the moving loop in the time varying B field. So the third case is when the loop is moving and the flux lines or the magnetic field is changing with time. So the flux lines are also changing. So in this case, as we said that total VMF, so total EMF, that is VEMF, will be equal to this is your motional EMF. So we can write a motional EMF plus the next EMF which is your transformer EMF. So both the EMF will be present into this equation. Okay. So this EMF is nothing but same, this is E dot dl. Okay, left hand side this is E dot dl. Now come to the right hand side case. In the right hand side case, if we talk about this first transformer EMF, so this both the EMF will be present. First is the transformer EMF, second is the motional EMF. So transformer EMF occurs when we have the stationary loop with a time varying B field. So this one is representing that. This is the motion, this is the transformer EMF. So we can define it here. This is your transformer EMF. Okay. So this is the transformer EMF like this one. So this case for this one is, this is the stationary loop. Stationary loop in time varying B field, in time varying B field. Okay. So this is minus del with the minus sign del B upon del T into ds. Okay. So now come to the second point. This is the motional EMF. So motional EMF is when we have the loop is moving in the stationary B field with the velocity of u. So here this is the motional EMF. So this is your motional EMF. Motional EMF, and the case for this one is when we have the moving loop in static B field. Okay. So this is your motional EMF. So this was your transformer EMF. This is your motional EMF. So combine of these two EMF will be there. This the total EMF is there. U cross of B. So U is the velocity by which the loop is moving into the static B field. So this B field is static. Okay, into DL. So now again we can see this is the open surface. This is your closed path. So what we can do, we can change it into the we can apply the Stokes theorem for this case, del U cross B dot DL, right. So for this case we can define it as the close for the Stokes theorem. So let's come for that for the Stokes theorem. So what we can use it here, so we can change here, so that we can define the what is the Stokes theorem for this case. Okay, so let's write it so that things will be clear to all of you. I am writing for this case only. Okay, so for this case, this is your close path U cross B into DL is equal to, with the open surface, it will become del cross U cross B into ds. Okay, so this is your closed path equal to the open surface, and this is nothing but this is your Stokes theorem. This is the Stokes theorem. So we are applying the Stokes theorem in this case. So what will happen? So in place of this equation, this term, we can write this way, because okay. So for this case also we can apply the Stokes theorem. So for this case, what we have, open surface del cross E into ds. Okay, so see, this is left hand side del cross E dot ds. In the right hand side, first term del dot B, del B upon del T dot ds. So ds also there, ds is also there. In this case we are using this equation, so ds is also there. In the left and right hand side we have both open surface, so we can compare these equations, left and right hand side. So what we will get? We will get del cross E is equal to minus del V upon del T plus use the del cross U cross B. So here we can write del cross E is equal to, so this equation we will get del cross E is equal to minus del B upon del T plus del cross U cross B. So this is the case of the total EMF in the case of the moving loop into the time varying B field. I hope these three cases are clear to all of you, and these three cases are very important for the exam point of view. So please try to understand, try to write the expressions yourself, so that things must be clear to all of you. So there is nothing much tough, because simply you must know how to apply the Stokes theorem in these cases, right? So if you are familiar with the Stokes theorem, then easily you can write these equations. Okay, so just simply you have to write the first equation, that is voltage EMF is equal to closed path E dot dl. So rest is same conceptual point which you can understand. So one of the question we can try it here, that a conducting bar that can slide freely over two conducting rails as shown in the figure. So we have to calculate the induced voltage into the bar. So here the loop is conducting bar which is sliding. Okay, so what type of the EMFs will be generated, we can think about that. First case, let's see, if the bar is stationary. So bar is stationary, it means the loop will be stationary. When the loop is stationary, it is defined like this, and B is this one. So we can see there is a B is not constant, there is a time varying B field is there. Okay, so it means the loop is stationary and the B field is varying. So what is the case for that? The EMF which is generated, that is a transformer EMF, will be generated in this case. Okay, second transformer. Okay, so this is the transformer EMF case. Now come to second case, if the bar is slides at the velocity u and the B is 4AZ. It means B is not the component of the T. So B is stationary. So this is the case of the motional, this is the motional EMF case. Okay. So the EMF which is generated, that is the motional EMF. Now come to third point. If the bar slides at the velocity, with the velocity, and the B is like this. Okay. So we see in this third case the loop is varying. So loop is varying means when the slide bar is moving left and right hand side, it means the size or the surface area of the loop will be increase or decrease. So in this case, what will happen? The loop size will be increase or decrease. It means it is varying in nature, and the B field is also moving with changing with the time. So it means in this case the transformer EMF plus motional EMF will be present. Okay, both the EMFs will be present into this case. So this transformer EMF, this the motional EMF is there. So addition of these two EMFs will be present into the third case. Okay, so I hope this point is clear to all of you. So here we see the direction of H. So the direction of B is what? Direction of B is the outward, right, outside the board. So okay, easily we can see that VEMF, we know this formula, minus del B upon del T into ds. So as the range of y will be 0 to 0.08. So this is the y 0 to 8. So we can convert this 8 centimeter into the meter. So 0.08 is there. So this limit is there. X is 0 to 0.06. So we can see it here. So x direction is this one, y direction is this one. So x is, we can convert it. Okay, so simply just put the values, and I assumed that you all are very much familiar with the integration. So please try to solve it yourself, then things will be easy. Second point, V EMF U cross B, U is given, B is given. So simply you have to put the values. So range for that one, that is L to 0. So just put it, and then finally you will get the answer. The length, everything is given into the question, UBL, that is 4.8 millivolt. Third case, because as we so this is the motional EMF which we are getting, right, in the second case. Third case, both transformer and motional EMF is there. So formula is same. Simply you have to find the psi value, and total flux will be equal to B dot ds, and just apply these cases. Then psi y 0 to y and x 0 to 0.06. So because y is variable, so this y you have to write this expression in terms of the y. Similar to that, then just put the value dy upon dt, because we know this value is a u, and here the ut is. So we see here that we have to put the values of dy upon dt. So total EMF value will be minus del psi upon del t, n is equal to 1, because there is a one loop is there. So when you put all these values all together, then finally EMF which is generated like this. So the expression which we get for the total EMF, that is EMF for motional and the transformer EMF is there. Okay. So I hope this point is clear to all of you. In the next lecture onwards, we will discuss about the displacement current. Okay. Thank you very much.